Good afternoon, everyone. Today I want to talk about the elliptical initial data solver. This is a work that we have done with our collaborators. I've listed them here. Before starting my talk, I want to thank you, the organizer, for such a great event and this opportunity for me. First, I want to start with a quick introduction of what is the importance of the initial data by asking this question that what role initial data playing in the numerical relativity. Then I'm going to go a real quick introduction for the formalism that we use to solve initial data, which comprised of the Einstein's equation and Euler's equation. Then I'm going to talk about the numerical method that we are using to construct initial data and algorithms for getting to a converged solution. And finally, I'll show some results and tests of this code and the future plan that we have. Okay, first thing, why do we do numerical relativity at the first place? Let's imagine that tomorrow we go to LIGO and we get an observation and we want to interpret this observation. So how we can do this observation, we can do this interpretation. So for that, we need accurate theoretical models. So if the objects are far from each other, we can do some post-Newtonian approximation, and it is working. And if the objects are merged, then after merger, so we can use some perturbation theory to interpret the result. However, if they are about to coalesce, the matter and gravity are in their most dynamical and nonlinear forms, and all of these approximations are breaking down. So we do need numerical relativity to understand the physics here. Furthermore, we know that the detector sensitivity are increasing, and also other detectors, new detectors are coming. So I want to emphasize on the importance of the numerical data for like next decades. So for example, if you look at the figure 1, the yellow signal showing gravitational wave of GW, like similar to GW 150914, that observed by LIGO, which is upgraded LIGO. And the blue signal is the one that getting like hypothetically received by a cosmic explorer. So, and as you can see, the noise is much lower in cosmic explorer, and or in technical terms, the signal to noise ratio is much higher. So we do need accurate numerical relativity to get the hang of this result and interpret this observation. Okay, so the general method, like that, we do the numerical relativity simulation, as this morning was mentioned by Dr. Wittek. So we split the space-time into a stack of hypersurface spaces. Okay, so and we label them with different time, like sigma T0, sigma T1, sigma T2. And what we do is we take one snapshot of all of the fields that we have at, let's say, sigma T0, and then we give this data to a time integrator, to some evolution code, and we march through the time. And this is generally the way that we do the numerical relativity simulation. And the challenge here is to constructing self-satisfying, constraint-satisfying and self-consistent initial data. And this is what Elliptica provides. So Elliptica construct, let's say, a snapshot of the system at this particular slice, and then it passes the data to an evolution code, and the evolution code will do the rest. All right, what equation we are solving here? So just real quick, in the context of 3+1 formalism, we take the metric in that particular form, and we project Einstein equation, and using the conservation of SS energy tensor, we we derive the Euler's equation plus some quasi-equilibrium assumption and conformal decomposition. Altogether, we cast the initial data, we cast this equation into elliptic and algebraic forms. And real quick, I mentioned them here. So the thing that I want to turn your attention is the nature of these problems, the nature of these equations. So if you look at equation number 2, 3, 4, they all have like some Laplace operator here. Okay, also here, unless the last one, which is just algebraic equation. And the way that we solve this, this equation is through a Newton-Raphson method that I will explain shortly. Just for the sake of completeness, I also add the boundary condition that we use for this equation. And for example, at the surface of the black hole, we impose some boundary condition to guarantee that we have a black hole at that area. And also at the surface of the neutron star, we do need some boundary condition. And at the outer boundary, we should also impose some boundary condition. Altogether, these previous equations and these boundary conditions here, if you solve them, so you get the initial data solution. However, this is not as simply as just solving this equation because many things can go sidetracked. And in fact, one of these things that make the situation more complicated is the existence of this algebraic equation. Equation 5 and 6, okay, together with other equations kind of showing how the matter is distributed. Which these two equations, 5 and 6, mostly being solved challengingly inside the neutron star, which we have the matter. So I'll point out some of the challenges later. Okay, so all right, so you give the physical parameter to your system, okay, and Elliptica goes and solve this equation such that all of this parameter, the physical properties that you want, reach to this target value that is specified. This is the gist of the whole idea. Okay, let's get into a little bit of more details about the numerical method that we use. Let's say you want to solve a simple Laplace equation, one dimension. You have a Laplace operator here, and you have, let's say, source together with a boundary condition on a grid omega. And we know that Laplace equation with given boundary condition has a unique solution. Generally, the way we do it is, as I said, it's a Newton-Raphson method. You compute vector f at all of the grid points, which is the difference between the Laplace operator and source inside the grid. And for the outside of the grid, you use this boundary condition that you want to satisfy, and you use and you make another similar vector f. Okay. Then the next step is to find the functional derivative of this vector f with respect to u at all of the grid point, which computing the Jacobian matrix. And then what you do is you solve this metric equation, j u tilde equals minus f. You find the answer u tilde, and you update your initial guess. You keep going this process again and again till to reach some criterion. For example, the number of iteration if it exceeds some number, or if the tolerance of this vector is lower than a specific prescribed value. However, this algorithm is expensive because if you want to compute this Jacobian matrix, or when you want to solve this matrix, a lot of resources required. So the bottlenecks of this algorithm is step 4 and 5. And to speed up these things, we have some solution for that. Okay, first thing, why, first of all, the computation of this Jacobian matrix is expensive. So imagine that you wanna, generally the way that people compute this matrix Jij is through some approximation, some finite difference approximation. You vary the value of the field at a specific at all the grid points, and using equation 14, you approximate the value of the Jacobian matrix. And if you calculate this, the time complexity of this computation is at least n cross n times n ln of n, because for each change for j, you should do at least one fast Fourier transformation, and you should do it at all the grid points. Okay, and also you should notice that this is an approximation calculation. It's not accurate, and the better that you can approximate the derivative in the Newton-Raphson method, the faster you can get to the root of the equation. What we are doing here, we use some spectral expansion, and we derive Jij analytically with lower time complexity. So I don't want to go to a lot of details, but equation 15 is the very last result that you can get when you are computing the Jij. And as you can see, it has like a compact form, it's analytic, and has like a lower time complexity, and it is n square. So this is the first point like that we introduced to increase the speed of Newton-Raphson method. So the other thing is, when as I mentioned earlier, when you want to solve the matrix equation, this operation is very expensive. Let's say for a production run, you have a big matrix like 10 to the 5 times 10 to the 5. And matrix solver are not scaled like linear. So, and performing worse when you have a larger matrix. And generally people what do is using iterative solver, and for that you should have some preconditional. However, the idea that we have is, instead of solving, let's say you have a grid here, you have a grid is 4 times 7, number of grid points that you have here. And if you want to solve this equation here, so you have 4, let's say you have like 4 times 7, but as I said, it's the bigger dimension that you get, your performance is going to be worse. So instead of solving this for a whole grid, you can divide your grid into 2 subdomains, let's say omega 1 and omega 2, with some boundary condition here. And as such, you only solve the equation on omega 1 and omega 2. So as you see, the dimension of the matrix here would be lower than the original matrix. Okay, the price is you should have some boundary condition here. So you should impose equation 16 and 17, which is nothing, just having continuity of the field and the normal derivative of the field across this region. However, as I will show later, this is not something that we introduced to the code. So we already have this kind of boundary because we are not covering the whole grid with only single patch. So we already have like many patches that cover the whole grid, and we actually use this property to efficiently solve this matrix equation. And also, if you remember, I told you that the Laplace equation has unique solution if you have the boundary condition. So if you know the value of the boundary here and here, you can solve in the parallel fashion the whole matrix equation. So it's a huge speed up for solving this kind of equation. And in fact, in Elliptica, I'm not using any iterative solver. I'm using direct solver, like UMF pack. Okay, so let's say we split the grid in omega 1 and omega 2. If I write the matrix, the Jacobian matrix J, as it is, I'll end up with a matrix, something as shown in figure 3. So as you can see, the bulk equation and the boundary equation are mixed up. And I cannot see like how this matrix can be solved in a parallel fashion and in an efficient way. So to kind of see that, to make this matrix block diagonal. So we arrange the equation, and what we will get is something like figure 4. We separate the bulk equation and the boundary equation. So if you see at this area, we have a block diagonal matrix. So it means that if I know the values of the omega-1 and omega-2 here, then I can solve the rest of the matrix, which has much lower dimension with respect to the original matrix, not only in a parallel fashion, but in a very fast method as well. So in a mathematical notation, we reorder the Jacobian matrix such that all of the bulk equation appears here, and the rest going to be the boundary conditions. And however, there are very sparse, and many of these matrices are 0 because we do not have boundary condition between one of the patches that's here and the other patches is far away. They only sharing. They only have boundary condition if they are touching each other. And at the end of the day, the way that we solve this matrix 18 is looking at this equation, 2 equations and 2 unknowns. And if you look at equation 19, I can expand it into for the first row, for the v tilde and for omega tilde into 2 equations. I can write v tilde in terms of omega tilde, w tilde, and I can substitute w tilde into the next equation. And the final result is a matrix equation, which has only w tilde as unknown. So after finding the w tilde, I can substitute back to the equation 20 and find all the value of the v tilde. And yeah, and this is the gist of the Schur domain decomposition method. This generally is divide and conquer method. Yeah. All right. So this is the patches that we use, this cube spherical coordinate that we use to cover the computational grid. So here on the left side, I'm showing the neutron star, and on the right side, this is the black hole, which we excise from our computational grid. And the rest is just the space between them and the boundary condition here. So, and as I mentioned earlier, what we do is we impose some boundary condition here, and we find the values of the boundary first, and then we use all of the cores that we have available in the system, and each of them going to find solution in each of these patches. So, and that's how we speed up the solving of elliptic equation. All right, so this is how we solve elliptic equation, but this is not the only things that you should solve. You should also do other things. Because let's say you want to have a specific spin for your black hole, a specific mass for a neutron star, and also you want to have specific at a specific distance. So you give this parameter to the Elliptica, and Elliptica goes through this algorithm to not only solve this elliptic equation and find the correct distribution of the neutron star, and just remember that when you have a neutron star and a black hole, because of this tidal forces for the black hole, the neutron star getting oblate. So you do not know in advance what is the surface of the neutron star. So you should also adjust at each of these iteration. You should also adjust the new surface of the neutron star. And remember that because we are using the spectral method, the matter should confine with a specific patch. Otherwise, you get Gibbs phenomena, and your convergence going to spoil. So the idea is that we first solve elliptic equation, we update the fields in a relaxed fashion, then we adjust the black hole, spin, and then we adjust the mass of the black hole, we adjust the neutron star mass, we adjust the center of mass. This is the other things that we should do because we want to have a 0 ADM linear momentum. When we want to extract the gravitational wave, it's better to have a 0 momentum. Otherwise, it's going to have some side effect on extraction of gravitational. Then we update the enthalpy, and by that time, maybe the neutron star center is drifted. So you should bring back the neutron star to a specific point, and then you should find the new surface of the neutron star, because when you update enthalpy and all of the other fields, as I said, because of these tidal forces, the surface also changes. Okay, so you after you find everything, you create a new grid, and then you interpolate your fields from the previous one to the next one, and you do this iteration over and over, reach to reach a specific criterion. For example, when you observing that the constraint, like the Hamiltonian constraint, is not changing anymore, it's reached to some truncation error that you expect. Then you change the resolution. You go to the next resolution, and you do it as much resolution as you want. All right, so let's illustrate some of the tests that we have done. So maybe the first test that one should do in the when dealing with the spectral code is to verifying the spectral convergence of the code. Here on the left side, figure 6, I'm showing Hamiltonian momentum constraint for a configuration that I shown on the caption of the figure, which has like a specific black hole has 8.4 mass, baryonic mass is 1.4 for the neutron star, with 0 spinning and polytropic equation of a state with a specific distance between the two. And on the y-axis, I'm showing the L2 norm of this constraint, and the x-axis showing the resolution. Okay, and as you can see, the constraint, as I'm increasing the resolution, going down in the exponential way. The other test that we can do is to add a spin to the system. For example, looking at so we add a spin like this is the spin of the black hole is here shown with minus 0.46 and so forth, and also for the which gives you the magnitude of 0.8. The dimensionless spin of the black hole is 0.8 here, and for the neutron star it's about 0.45. Yes, 0.45, and they have like in an arbitrary direction. So this is one of the cases that gives you precision. And again, in this case, if you look at the constraint versus resolution, you will see that they are like going down exponentially. Okay, the other things that we done is to kind of finding how far we can go in terms of like a spin of the neutron star. And the analytic values for the breakup spin is about 0.7. And the maximum spin that we can get for the neutron star is about 0.63, which is about close to the breakup. And we plot the neutron star spin versus the parameter that we set in the parameter file to get the specific spin. The other thing is we compare our results with post-Newtonian approximation. So we add a spin onto the black hole, and this in the y-axis showing the binding energy and x-axis showing the total mass. And we compute the post-Newtonian plus spin orbit interaction, and this solid line showing the post-Newtonian result. And the dot here, so over all of these curves, showing the result that we got from the Elliptica. And as you can see, the analytical result and what Elliptica calculated, they are agree with the specific error that we have in our computation. Okay, so before moving to the evolution part, the way that we set up this initial data is using the excision. It means that we excise this area, okay, from our computational grid, and instead we are imposing some boundary condition on this side. All right, so if we want to use the moving puncture method, it requires to have data all over the grid, not only like here, so everywhere, including this area. So to do that, we fill this area with some data, and the idea is that we extrapolate the fields that we have around the black hole inside to the black hole. So the function that I'm using to do the extrapolation is this function, which has, like, in the radial direction has a Chebyshev polynomial, and in the spherical position direction has a spherical harmonic. So so the challenge here is to find the coefficient of this expansion. After you found this, you can fill this this area, this exercise area, with this function. The way that we find this coefficient is by requiring to have, like, a smooth transition when you are crossing this this horizon here. And so for that we require to have, like, the value of the field be continuous, and also the first and second derivative of the field in the radial direction also be continuous. Also, for if we also the other derivative, the higher derivative, we set it to 0. At the center, we require to have a value which is a constant, and generally the value is promoted by having the value close to the moving puncture method. And also we impose the derivative of the field at the center of the black hole be 0. And this is motivated by having symmetric as, because if you want to extrapolate the field from the left side and also extrapolate the field from the right side, they might end up with different points. So in order to have, like, as much as symmetry, so we also impose yet another competition at the center of the black hole. Okay, so we populate CNLM, this coefficient here, and whatever fields that we want for the moving puncture method, we use this equation to fill here. All right, so let's see how is the performance of this black hole field. Here on the this is the orbital plane that I'm showing you here. So this is the neutron star and this is the black hole, and the color line here is the Hamiltonian constant violation. So this snapshots here is taken at t equals to 0, 5, 25, 50, and so forth. The most important things are these few first snapshots. What I want to say here is that we use this black hole filler, okay, and we observe this constraint, and we see that this constraint, this propagation of the constraint out of this black hole that we feel it, is less or comparable in terms of, like, the magnitude to other violation that we have the rest of the grid. So in the other words, this black hole flare is a good candidate to be used. And after a while, we see that this violation propagating out, and we reach to the moving puncture method, and the constant violation is only focused at the center of the black hole, and it's trapped there and rest here for the rest of the evolution. So that's what we expect to have in the moving puncture method. So it performs very well, this black hole field. Okay, the other things that we want to have is extensity reduction, because let's say two compact objects are like million years away from each other, and because of this gravitational wave, the extensity of the system is shed. So so nature generally provides us a circular orbit, and but when we construct initial data as with this algorithm, we might have some eccentricity, like a small eccentricity in the system. So we should have some algorithm to also reduce the eccentricity of the system. So the way that we do this, we adjust omega and
10 minutes.
And radial velocity, and also the radial velocity to drive the eccentricity of the system to acceptable value. For example, here I'm showing the zero eccentricity that we have right off the bat when we construct data with the approximation taking place there. This is the blue curve here. We use this eccentricity reduction method, and as you can see, the eccentricity going down to 3.8, 10 to the minus 3, and then 3.4, and then finally less than 10 to the minus 3. And on the right-hand side, this is the orbits of the same system with the last eccentricity that we achieved. And as you can see, they are like very circular and nicely merging here. The other test that we've done is extracting the gravitational wave. So I should first say that we do this evolution with BAM code. Okay, we done the evolution and we extract the gravitational wave. And this is the gravitational wave. We compared our gravitational wave with also the gravitational wave of the same system from the other code SXS. And as you can see, they are like lying on top of each other. So this is another test that the system is working. Also, as you know, after supernova explosion, the neutron star can get a kick, and so its spin can get changed. The orientation of the spin can get changed. Also for the black hole, the same. So the other test that we done is to look at the orbits of the precessing system. Here I just mentioned the configuration of the system here, and we did the run with the BAM code, and as you can see, we have like orbits which are precessing. Okay, so in a summary, I want to say that elliptica supporting a wide range of physical parameters, like high spinning black hole with arbitrary direction, high spin neutron star with an again arbitrary direction, polytropic and piecewise polytropic, various mass ratios, and high compactness neutron star. Also, it has efficient eccentricity reduction, efficient black hole flare to be used for moving function methods, and also has a fast and robust elliptic solver. As I said, it's using analytic and fast computation of Jacobian, and also has a rapid and robust matrix equation solver using Schur domain decomposition. The future plan that we have is to study more black hole neutron system for wider physical parameter, and also testing and improving our gravitational wave models along this line. Also achieving, as I said, elliptica limited with high spinning black hole. So it currently can reach to 0.8 dimensional spin, but it is ideal if we can get to even higher spin, like extremal, like 1. And also, I'm interested to work on the extension of constructing the initial data for extension of formalism for general relativity. And the other things that I want to mention, so since I have like a little bit of time, is the parameter phi for the elliptica. So here, the way that we do that is okay. So the elliptica is has like project by project. So you have like one project for neutron star, one project for the black hole, and you combine them, you get the black hole neutron star system. And if you want to get the 2 neutron star, you combine 2 neutron star project to get binary neutron star. Okay, so you set the value of the project over there, and then you specify the grid that you want and where you want to reside your neutron star black hole, and you set the separation, you set the irreducible mass of the black hole, you set the chi value or the dimensionless spin of the black hole. Then you go to neutron star, you set the baryonic mass.
5 minutes.
You also set the equation of a state for the neutron star. And so, for example, here I just set it polytropic, but it could be as well piecewise polytropic. And you set the parameter for the neutron star. And yes, and then you just, and the other things to how to solve these equations, and then how you want to like adjust the update of your fields after each elliptic solving. You pass this parameter file to Elliptica, and Elliptica reads it and give you the initial data in a binary format. Okay, I guess I'm done here. Yeah.
Great. All right. Thank you, Alireza. All right. So we did have a question in chat that appeared, and that is, what's the minimum separation for equal mass non-spinning black hole neutron star initial data that Elliptica might be able to produce?
So the minimum separation. So let's think about that. So in terms of orbit, I guess we can have like a less than one orbit. Yeah, I can maybe answer this.
Oh, wow.
Yeah.
Less than an orbit.
Yeah, less than orbit. Yeah.
Wow. That's pretty impressive.
Like about orbit or less than orbit.
Yeah. So I had a question.
Yes. Also, I forgot to mention. So I plan to make this code open source, and already talked to Zach and Ron Haas for making the reader for Einstein. Yes, and then so I'm looking forward. Yeah.
Awesome.
Right. Yeah.
That'd be wonderful.
Yeah.
And yeah, so if the reader is open source, then that presumably means that you'll make a library of initial data available as well. Is that correct?
Yes, that's it.
Awesome.
Yeah,
that sounds awesome. Good. All right. So I did have a question, and that is, so when you actually put the black hole data on the grid, the black hole data that whose interiors have been filled with sort of junk data, constraint violating data.
Yeah.
Junk is too strong of a word. Constraint violating data. Let's put it that way.
Yes.
Yeah, yeah. Filling the holes.
Yeah.
Okay. Yeah. So when you use your apparent horizon finder on it, do you find a consistent spin parameter to what you expect from what you input into this parameter file into Elliptica?
Yeah. So first of all, because we compute the spin on the horizon of the black hole, the Elliptica. So, and I'm not touching the data on the surface.
Right, but
so
my question is when the apparent horizon finder, after say 10-20 m of evolution.
Yes. So actually, yeah. So this is the test that regards mostly in the evolution part.
Partly, but it also measures the impact.
Minutes.
The filler.
Exactly.
Yeah.
And so for that, as far as I remember, I had maybe a few percent error, less than few percent error. The measurement of the spin done by band and also by the Elliptica. So only in terms of few percentage.
Great. And irreducible mass, similar?
Yes, similar. Yeah.
Cool. Any other questions? Roland.
Yeah. Given your home institution, how close is Elliptica actually in the end to SBIRD?
Yeah. So in what perspective exactly?
I mean, I assume.
So first of all, that's to only do the binary neutron star. So SQL does only the binary neutron star. So I'm doing black hole neutron star. Yeah. So, but
it's also a more modern implementation, I hope.
Yes. In terms of cube spherical, so we have pretty much similar cases, but in Elliptica,
1 minute.
Yeah, I'm covering the outer boundary in a better way, in a more symmetric way. And in terms of the project, so each small piece of this algorithm implemented in separate project. So in practice, you can you combine each of this small piece of the project to get a bigger project. So this is another difference.
30 seconds.
And in terms of Newton solver, also I'm using the spectral method and also using this Schur domain decomposition, which capable me to use direct solver. But in SQL using the iterative solver, GMRES, and for preconditioner using some direct solver. Yeah. But in terms of formalism, we both using extended conformality sandwich and the same formalism developed by Wolfgang for the high spinning neutron star.
Yeah, I just have a very quick yes/no question. Tabulated equation of state support for nuclear matter.
So
Do you plan it?
Yeah, I plan it, but it should be easier. So it'd be good, yeah.
Knock on wood. Knock on wood. Okay, great. Well, let's thank